All right, so let's go ahead and start learning by learning how to send this message, which is as follows, and I'm going to ignore the spaces for this one. My message is nom nom banana banana banana. So suppose you want to send this to a friend using Huffman encoding, okay? So the first thing we need to do is come up with a frequency table for this particular message that we want to send, all right? Which means counting up how often each letter occurs. So let's start with O. O occurs 3 times. M occurs 1, 2, 3 times. Okay? N occurs 1, 2, 3, 4, 5, 6, 7, 8 times. Okay? N occurs 8 times. We've got N, M, O, and now B and A are the last things. We got 3 B's. Okay? And then we got 1, 2, 3, 4, 5, 6, 7, 8, 9 A's. Okay? So what we do, so now we don't need our original message anymore, so I'm going to go ahead and just erase it, right, just simply to make myself more room. And now what we do is we create essentially a tree node that contains the symbol and the weight for each of these values, right? So we'll create a node here, and I'll represent it just by writing it over here. So, actually, I won't draw it just yet. And what we're going to do is we're going to place these nodes into a priority queue, ordered by from the least weight to the highest weight. And if in case of ties, we'll break it alphabetically. So B is the least weight, so it goes in front. Then it's followed by M, because that comes next in the alphabet. Then O, then N, 8, and A, 9, right? Sometimes things are going to be tied, and so we're just going to need a policy to break them, and so I'm breaking them alphabetically. Okay, right? Everything's, that's the frequency of our document in order. So now the algorithm for constructing it is as follows, right? While there's more than one item left in the queue, the first thing we're going to do is dequeue the first item. We'll call it left. Dequeue the second item. We call it right. So we dequeue the first item, we call it left. Dequeue the second item, we call it right. And then we're going to create a new node, one with no symbol, but it will have the combined weights of left and right. Make left the left child, right the right child, and we reinsert it into the priority queue, which now gets completely reordered. So let's go ahead and see that happen. Right? This is actually a fairly easy process, and if what I said before sounded like gibberish, it should start making sense once we go through this once, believe it or not. Okay, so let's go ahead, grab B. It has a weight of 3, right? D has a weight of 3. So we dequeue that. M has a weight of 3. We dequeue that. Okay, and we combine them into a new node with no symbol, but a combined weight of both of them. And so then we reinsert this into the priority queue. Now, because it's a priority queue, what I see a lot of students do is they make a mistake and they put it right here at the end, which is where it goes at first, but because it's a priority queue, it will reorder. So it goes in between the 3 with the O and this N over here, because we order it by the weight. All right? And then we just continue until there's only one left. Okay? So this is our tree so far. All right? So now we've got 3, O, and 6 dash. We make this the left child, make this the right child. So we dequeue them both. 3 and 6. So the left child. O. 3. Combined new node with a combined weight of 9. So we insert this in the back over here. Okay? The next thing we do, and we're going to just assume we rate ties alphabetically, and A comes before something with no symbol, so we are going to go ahead and do N and A next. So pop off N, pop off A. N has a weight of 8. A has a weight of 9. The new combined node has a weight of 17, right? And we will reinsert this, and now we reinsert this node into the queue. So we've got 2 trees over here, but that's fine because our next step says, let's go ahead and dequeue this symbol, dequeue this symbol. So we're going to make this one the left one, this one the right one. So I guess I should draw this one over here. 17. That was N8, B, what was it? It was A9. And we combine it into a new thing with a combined weight of 26. Right? What's interesting is now we're done. And what's interesting is that this weight of 26, it's 3 plus 3 plus 3 plus 8 plus 9. It's the combined weight of all the symbols in the tree. So this is done. This is our encoding tree. Now, how do we actually encode a message? So first I'm going to erase the weights just to get them out of the way. I don't actually delete them, but I get them out of the way. For the next step, we're going to mark all the left branches with 0s and all the right branches with 1s. Right? All right. That's the idea there. All right. So now to encode the message om nom nom banana banana banana. Okay. The first thing I need to do is that I just figure out what is O going to be. O is going to be, well, we start at the root and then we find our way to O, which is 0 0. So O would be 0 0. Now we need to do M is next for That would be 0 1 1, right? Because the branches we would follow would be 0 every time we go left, 1 every time we right. So 0 1 1 and so then 1 0 for NO, 0 0 for O, and then 0 1 1 for M. 0 1 1 for M, and that's the beginning of our message, right? And we'd continue doing this for every single character in om nom nom banana banana banana, right? So on and so forth. And so then we'd send this tree to whoever we want to decode this, and then we'd send our bits, our encoded message here. And so the person will look at this at our bits and they'll go, okay, so how do I decode this? How do I decode this? 0 0. So I see a 0 and then I see a 0 and then I get to a leaf node. So that means that these two, that 0 0 is an O. So let's start here. Then let's start here. 0 1 1. And then I go 0 1 1. That's an M. And I go 1 0 0. Sorry, 1 0. That's an N. Okay? Then 0 0. It's an O. Right? Then we get 0 1 1 for an M. So we got nom, and so on until we decode the message. So the way you decode a message is that you basically, for every bit you see, you decide to go left and right until you get to the very bottom. Once you get to the very bottom leaf node, you stop. Right? And then you say that's what that particular character combination was. So that's the way that works. Now notice that the least common characters, N and A, are 2 bits each. And the most common characters, N and A, are 2 bits each, whereas B and M, which are more common, are 3 bits. NO also has 2 bits, even though it's got the same weight. But that's just simply a consequence of it being later in the queue. Since it was later in the queue, it was assumed to be more frequent, even though it was tied, right? So these guys at the bottom of the queue, they take up the most bits, all right? So let's go ahead and now take a look at our let's take what we know and look at the slides again.